Welcome to Math 2320, Section 6.2. We're looking at power series representations, and in this particular section, we are looking at things called ordinary points. So what does that mean? So in problem 1 here, we have a differential equation. We have variable coefficients, and so we put it in standard form. So I divide through by the lead coefficient and I get something in front of y prime. We call that p of x. I get something in front of y and that's q of x. So we have this thing called an ordinary point if both p and q are analytic at that point. So what did that mean to be analytic? That means that it has a power series representation. And if it has a power series representation, then it has derivatives of all orders. So looking here at question 1 now, I see that because of this denominator, it could become undefined at places, so that's factorable, into x minus 8, x plus 8. So it has roots of minus 8 and 8. So at x equals 0, which is an ordinary point because these particular item p and q are defined there, they only blow up at minus 8 and 8. So for x equals 0, the radius for the solution to be looked at is 8 because here's 0, distance is 8. Whereas here for x equals 1, the radius between 1 and 8 is 7. So again, to be an ordinary point, both p and q are analytic at that point. Alright, so in question 2, we have a second order constant coefficient differential equation. We could easily solve this by the methods that we've seen in chapter 4. I could form the quadratic equation, factor out the m. I get m is 0 and 1, which gives me that the solution is c1 e to the 0 plus c2 e to the x. E to the 0 is just 1, and so my solution would be of this particular format. Easy enough. So what would this mean if we were looking for solutions of the power series form? All right, so let's take a look at that. All right, so we have our differential equation. We assume it has a power series representation. The first derivative, the initial C0 would be 0, and I would just start off with C1 to C2 and so on. So the index would start at 1. The second derivative, I get another exponent to come in the front. We would drop the exponent by 1. Again, the first term would be 0, so the index would start at 2. So to keep everything with a similar index, I re-index things. And so if I let k be n minus 1, that says k plus 1 is n, and so then I could relabel. Alright, so let's take a look. And so by doing that, we have this situation, and so put everything together. So I've got y double prime minus y prime. So I put in my terms for y double prime minus y prime, factor out the common x to the k. Now, because this thing is supposed to equal to 0, that tells me that this term has to be 0. So therefore, I set it equal to 0, move the ck plus 1 to the right hand side, isolate the ck plus 2 term, giving me this relationship about ck plus 2. All right, so we did that. So here is that. Factor out the k plus 1, giving me the final form. All right, so when k is 0, what does that mean? Well, when k is 0, I get 1 half C1. When k is 1, I get C3. When k is 2, I get C4. All right, but notice each of these is in terms of C1. All right, so what does all this mean? So here we go. Y of x is y1 plus y2. We know that. We know it has a power series representation like the following. All right, so filling in what I know I've got a C0, C1x plus, and now starting at C2 term, we have this relationship, C3, C4, and so on. So now I'm going to take the terms that have C1 in it, I'm going to factor it out, and I get this relationship. Now at this point we're almost there, but I need to recognize that e to the x has a power series representation that looks like the following. It should have a 1 as a leading first term. Alright, so to fix that up, I'm going to take this piece and add in a 1 and subtract a 1. I'm going to keep the 1 and the rest of this together. And so this is really C1 e to the x. I get this C0 minus C1. All right. And so what I'm seeing here is that I can think of this as 1 and this particular term over here as minus 1 plus e to the x. So it does match with the solution we would have got a lot easier a different way. All right, in question 3, we repeat the same process. So we have our power series, our differential equation. I assume a power series solution. I get y, y prime, y double prime. Again with our indexing. All right, so I fill everything in, multiplying through. In this case, I have an x. All right, when I multiply this x in, that's going to give me an x to the n plus 1. All right, re-indexed here back to 0. Got that. This one we kept everything like it was. So now I'm going to re-index again here. All right, and so eventually I have to come in here and figure out what my coefficients will look like. So coming down here, all right, I take off the lead term. So when k is 0, I get a 2, a 1, and a C2. So that part, so that's what went on right here. And I get that piece out in the front. This one starts off at 1. And I did that so that I could get this x to the n plus 1 back to x to the k. to match this x to the k so I could factor it out. Just like we did in the previous problem, so we can get our hands on this part. So this is supposed to equal to 0 again. So this is a term in front of the x0 term, so that part is 0. This part is supposed to be 0, so again get a relationship between ck plus 1 and in this case ck minus 1. Alright, so recopying our formula, let's see what's going on. C0 I don't know, C1 I don't know. We saw C2 was 0. So that starts off at C3. C3 comes when k is 1. So I plug in k equals 1 and I find out C3 is minus 1/6 C0. Do the same for k equals 2, get C4. See that its relationship is with C1. C3, which is C5, involves C2, but C2 was 0. You have to be careful because of all these indexes going on. You have K running, that gives you a particular C, but then that's essentially several 3 away from where ck plus 2 was. Do the same for K4, giving you C6, which involves C0, K5, C7, and C1. K equals 6, which is C8. C8 involves C5, but C5 was 0. So trying to put all this together by grouping it in terms of the things that have C0 in it and the things that have C1 in it. So factoring out the C0, that gives me my y1 of x. Factoring out the C1, that gives me my y2 of x. Yes, it does seem a bit tedious and torturous, but it does work. Alright, in question 4, we have our differential equation. Our term, our variable term in this case, is a sine. So a lot of this is what we've done before, assuming the power series, getting the first and second derivatives, and then plugging things in. Now, the added difficulty here is my sine term. I'm going to get its power series representation, and that's multiplied by y. Alright, so filling things in. So here's my second derivative. Here's the sine piece. Here's y, which was our power series representation. Alright, so let's put in some terms and see what happens. So I fill in. N is 2, N is 3, N is 4, N is 5, so I get a flavor for what's going on. Here's my sine, here's my power series expanded. All this is supposed to be 0. So let's group some things together. Alright, I've got 2c2. It's the only term without any x's in it. I go looking for all the x terms. I got a 6c3. Alright, I'm going to have an x times c0. Alright, there's that term. What about any other terms? x2, x squared. Let's see. a 12c4. How am I going to get an x squared over here? Well, let's see. I'm going to get an x times this c1x. And then when you go to the cube, you're going to get a cube from this part. You're going to get a cube from x times the c2 x squared. You're going to get an x cubed times the c0 term. So all of these pieces have to equal to 0 because it equals 0 on the right hand side. So that gives you all these solutions to C2, C3, C4, C5. All right, so putting that all together, what we just now know about C0, C1, C2, C3, C4, C5, and so on. And then grouping together all the things with C0 in it and factoring it out. Putting together all the things with C1 in it and factoring that out. And so that gives me my y1 of x and my y2 of x. So be careful in this section and in the next section because it's very easy to lose a sign, a constant, an index, so go carefully.